Two wide rings of high-intensity particles encircle our planet's equator. Known as the Van Allen radiation belts, their behavior in response to the sun directly impacts life on Earth and in orbit.
We live in the atmosphere of the sun, so when the sun sneezes, the Earth catches a cold. So whatever is happening on the sun, the Earth will feel an effect and will respond to that changing space weather.
NASA's two-year Radiation Belt Storm Probes mission aims to study this ever-changing space environment in greater detail than ever before.
Definitely the biggest challenge that we face is the radiation environment that the probes are going to be flying through. Most spacecraft try to avoid the radiation belts, and we're going to be flying right through the heart of them.
The mission's twin probes will help scientists characterize changes within the radiation belts. An advanced instrument suite on each probe offers a complement of new state-of-the-art tools in the quest to learn more about this mysterious and powerful region surrounding our planet.
So the radiation belt storm probes will actually give us a better understanding of how the radiation belts actually work and allow us to do a better job of predicting and protecting against the radiation that's up there in the future.
The discovery of the radiation belt dates all the way back to 1958. That's when NASA launched its first spacecraft, Explorer 1, built by James Van Allen and his team from the University of Iowa. More than a half-century later, RBSP will carry an array of instruments designed to measure the properties of charged particles speeding through the radiation belts, as well as the plasma waves, electric fields, and magnetic fields that transport and guide those particles.
There are particle instruments that literally go from very, very low energies around the plasma energies that we're very interested in, the slow-moving, cold, dense plasma that we want to measure, up to extremely high proton energies that we see. They're the dangerous, very fast-moving, very high-energy protons that are in the inner belt. We also have instruments that measure both magnetic and electric fields.
The RBSP mission is part of NASA's Living with a Star program, which is managed by the agency's Goddard Space Flight Center in Greenbelt, Maryland. Built by the Johns Hopkins University Applied Physics Laboratory in Laurel, Maryland, the 8-sided probes are basically identical. Each weighs in at more than 1,400 pounds and measures about 6 feet wide by 3 feet high. But don't let their compact size fool you. The sensors measuring magnetic fields are mounted on booms that will extend nearly 10 feet from the spacecraft. And the electric fields instruments are set at the ends of long antennae, which will stretch up to more than 160 feet away, tip to tip, the length of a football field. These booms are tucked away inside the spacecraft during launch. They'll be deployed after the probes reach orbit. The long booms help distance these sensitive instruments from the immediate vicinity of the spacecraft's own electric and magnetic fields. Data filters and metal shielding on spacecraft electronics also helps prevent interference. The result is a magnetically and electrically clean spacecraft.
And so as we're going through these big solar storms and these high radiation environments, the instrumentation will just keep going, our data recorders will just keep going, and we'll be able to capture all that great information about what's going on.
But before RBSP and its science team can get to work, it has to endure the journey into space. This isn't the first time NASA's Launch Services Program has prepared 2 probes for liftoff. In 2006, the twin Stereo spacecraft were launched, and just a year ago, the launch team was gearing up for the Grail mission, which sent 2 spacecraft to the moon in September 2011.
For Grail, we were able to launch the 2 Grail probes side by side within the fairing, and that was because they were much smaller and about half the weight of RBSP. RBSP, larger spacecraft, we're going to launch them in a stacked configuration with the A spacecraft on top inside the Atlas V payload fairing.
The twin spacecraft are launching from Cape Canaveral Air Force Station aboard an Atlas V rocket built by United Launch Alliance.
NASA has an excellent history with the Atlas V rocket. As a matter of fact, we are 100% 6 for 6 launching on Atlas V. We have launched missions to Jupiter, Pluto, the Sun, the Moon, and 2 missions to Mars. So we're very excited with RBSP being the 7th NASA mission on an Atlas V.
During pre-launch integration and testing, working with 2 probes rather than the usual one was fairly straightforward for the team.
Essentially, for most of the processing integration, it's a single spacecraft. but when you get down to the aspects of the details of the separation and some of the on-orbit operations, it's 2.
After launch, each spacecraft will head off into a different orbit. That means the rocket Centaur upper stage has to spin up and deploy the first probe, and then stop the spin and move to a new orientation for release of the second probe.
Then you got to actually point in the right direction, spin it back up again, separate the second one, then you got to spin the Centaur back down again, and quietly back away.
The mission starts with a 60-day commissioning period so the team can check the probe's health and activate the instruments to ensure they are working properly. It's also when the team will extend the instrument booms away from the spacecraft.
Just like a figure skater, as they start putting the arms out, they're going to slow down. And so we spin the spacecraft up and do partial deploys on those booms, and then spin it up and do another partial deploy on those booms. And it actually takes about 2 weeks to get all of those booms deployed all the way out.
The orbiting probes will lap one another, traveling at varying speeds and distances, sometimes close together, sometimes far apart, but always within the radiation belts. Having 2 probes will give scientists a way to compare data and see whether each change they see is isolated or part of a larger trend.
So if you imagine having 2 buoys in the ocean, and one goes up and comes down again, you don't know anything about what caused that to go up and down. If both of them go up, then you know you've got a very big feature that is affecting both of them at the same time. If you have one goes up and then the other one goes up, well, you can measure how fast that wave has traveled between them and what direction it's going into. And if only one comes up and comes down again, then you've got a very, very localized feature that didn't travel anywhere.
The RBSP team has been working for 11 years to bring this mission to fruition. Launch day can be a bittersweet time after so many years of preparation.
There's a fair amount of nerves that go along with building a spacecraft, designing it, testing it. We're always finding things that could work better or don't work the way they should that we have to go fix. So once we get through launch and get the spacecraft up there and check them out, it's really going to be a great sense of relief, but a great sense of accomplishment too. We've got an amazing team that's been working on this for a long time.
I've had this mission longer than I've had my children. So for me, it's just, it's probably like sending your children to college or something. You know, you bring them up the best you can and then you push them out into the world. And I guess the good thing is mine will write home every day. It's fundamental physics with a practical application, and that's what makes this mission so cool.